Hi everyone, today I will present the paper Meta-HAR Federated Representation Learning for Human Activity Recognition. The authors are from University of Alberta and Tencent in China. Human activity recognition problem is the problem of recognizing human activity types based on mobile sensor data. The readings from the sensors such as gyroscope, accelerometer are processed and fed into a classifier to identify the current activity type. However, most existing works train models centrally with centrally collected data. Such works have two disadvantages. One is that it may cause privacy concerns because label samples may contain private user information. The other disadvantage is that we can only get a single model on the cloud side, which is inconvenient for mobile users. But with the growth of the computational power on mobile devices, federated learning has emerged as a decentralized framework for model training. It aims to train models based on decentralized data scattered on mobile devices without collecting them. In federated learning, a global model is first downloaded by each mobile device from the server. And then each user will train the model based on their local data set. And upload the local updated model for the server for aggregation. The central server aggregate the received models in a renewed global model and send back the model updates to the user's device. And then the next round is started. However, there are three major challenges to perform human activity recognition with federated learning. First is heterogeneity in label distribution. Federated learning will perform well if the training samples are independent and identically distributed across devices. But for activity signals, each user does not necessarily feature the same activity types. So the different activity types across users cause heterogeneity in label distribution. For example, one user may have walking and running recorded on the device, while another user may only have biking and walking because it doesn't own a vehicle. So in this case, the local training data set have unbalanced label distributions. And some previous work has shown that such a heterogeneity in label distribution across users can cause serious performance degradation. We can see an example here. The results show that the performance degradation can be up to 50% when learning on the non-IID data. The second challenge is the heterogeneity in signal distribution. Because two users may exist very different signal distribution, even for the same activity. The reason is because user may perform the same action in different styles. For example, two persons might have completely different working patterns, one with a large stride length while the other with a high frequency and a smaller step size. They also demonstrate with experiment that the heterogeneity in signal distribution alone can cause significant performance degradation. The data set they used is one of the data set they use in this study, and the original UH-AR data set is collected in a controlled situation, so it does not suffer from heterogeneity in label distribution. The only difference between the Fed average user and the Fed average shuffle here is the heterogeneity in signal distribution across users. The Fed average user is applied to the global HAR model across users, and the shuffle one is they apply Fed average to the global model where all the samples are first collected and shuffled on a server, then redistributed to all users. And we can.
So, Tongnian, so here, the Fed average in user, so they model, so in this case, they model a realistic heterogeneous singular distribution. So that's why their performance is not very good in Fed average.
Yeah.
And for the shuffle, so they don't have this singular that's heterogeneity in singular distribution.
Yes.
How can they do that? So they shuffle. What do you mean by shuffling here?
They first collect the samples and shuffled on the server and then redistributed to the users.
Oh, okay. So it's basically every user may have the same singular distribution because you shuffle them, so you randomly assign them to different users.
Yeah.
Oh, okay. Thanks.
And we can easily observe an accuracy reduction of the Fed average user compared to the central, while the Fed average shuffle does not have heterogeneity in signal, so it can learn a model that has performance close to the centrally trained models. The last challenge is that a single global model can hardly adapt and generalize well to individual users, especially to a new user with his own activity characteristics. So to solve the activity recognition problem on each user, the authors introduced a personalized output layer. And this layer, together with the global embedded network they proposed, forms a classification model that conforms to the local output dimension and activity set at each user. Before I introduce the framework they propose, I first talk about the mental learning. Mental learning refers to the learning about learning. A good mental learning model is capable of well adapting or generalizing to new tasks and new environments that have never been encountered during training time. The adoption process happens during test, but with a limited exposure to the new task configurations. And eventually the adapted model can complete new task. And the reptile is one of the simple mental learning algorithm. It works by rapidly sampling a task, performing SGD on it, and updating the initialization towards the training weight on that task. The author adopts a federated version of the reptile to mentor train the embedded network in a federated manner in this study. This is the framework they proposed. Its mainly consists of two parts: an embedded network and a personalized output layer. For the federated learning of the representation model, this is how it works. They treat the activity recognition problem at each individual user as a separate task, and each task has its unique input signal distribution, a different activity set, and even a different number of activity types. There are n users participate in the training, and there is a federated learning server and a new user for testing of generalization ability. Each user holds a local data set. They first pull the model parameters from the federated learning server and update them using its local data set. And then they push those updates to the server. And the server here is responsible for coordinating the collaboration process of all users and updating the global model. And as shown in the algorithm 1, suppose n users are involved with local data set. In each round, a subset of users is selected to update the global parameters. Each user, I first pull the current parameters theta C from the server and performs local training before pushing the updated model theta I to the federated learning server. And the server then average the collected updates theta I to update the global model.
Tongnian, can you just go back to the previous? So if you see the figure here, looks like each client's model consists of two parts. One is the theta, another one is W, right?
Yeah.
And when they learn, when they use the federated learning to learn the model, looks like they are only updating the theta, right? So you say that they're updating theta 1, theta n.
Yes.
So how do they update this theta? I mean, because this theta is just a partial, just a part of the overall network, right? So from this theta, you cannot directly calculate a loss function. Unless, if you consider theta and the W together, you will be able to calculate the loss function. Otherwise, you only get the output from the embedding network.
Yeah, they first get the output from the embedded network.
Yeah. So from the output from the embedded network should be able, you will use this output
Yeah,
to update your theta, right?
yeah.
So how do they update the theta? Using the output from the embedded network. That's my my question.
Oh, I
Yeah, if you say, Tongnian, you say the algorithm here. They
yeah,
say, I will train M, you need to read that, okay? They say train M epochs of the embedded network on local data set through Powell's loss, right?
yeah,
So
yeah,
basically means that they need to calculate this, they call it the Powell's loss, and then use this one to update the model theta. So
yeah.
this is maybe this kind of looks like different from the traditional laws that we are familiar with.
Oh, yes.
So what is the pairwise loss?
Oh, I will talk about this in the next slide.
Okay, okay, okay. Yeah.
So this slide will talk about the structure of the embedded network and the how it is locally updated by the individual users. For the structure, it leverages both the CNN and the RNN to process sensor readings. They first apply convolution to the stacked pair of magnitude and the frequency along each axis of each sensor signal. Then another convolutional layer is applied. And finally, they fuse the convolutional output of the different sensors through the last convolution layer. And finally, two LSTM layers are used to extract temporal relevance of the CNN output and output a fixed length embedding vector. And then by adding a fully connected output layer on top of the embedding network, we can build a classifier to get the predicted probability for each category. For the training process, they choose to train with pairwise loss. The pairwise loss does not require local users to be aware of the global activity set. So it's flexible and scalable to new activity types. It encouraged the clustering of sample embeddings in a real space. And first, they use the cosine distance, which is defined here, to measure the similarity between any two embedding vectors. And then the pairwise loss for the sample pair is defined here. Well, if AI equals AJ,
So what is the A here, AIAJ? Is that the feature, the original feature factor for I sample and J sample?
AI and H are the labels.
Labels. Oh, You mean the activity label?
Yeah.
Okay.
And the EI and the EJ here are the embedding output from the network.
Okay. Okay. So AI. So what does it mean for this pairwise loss? I mean, in terms of physical meaning, the loss IJ, I think it's more like the difference between sample I and sample J. So this phi, I forgot this phi or phi IJ is more like the difference in their embedding factors, right?
Oh, yeah. This one is the logistic sigmoid function. And if A1 then, equals AJ, this value equals 1. And otherwise it is 0.
Okay.
So
you want to minimize the you want to minimize the loss so that when user I when sample I and sample J they have the same label or same activity, their embedding should be as small as the difference should be as small as possible, right? If you check the value here, right, as you mentioned, if AI equal to AJ, then this delta AI AJ would equal to 1, right?
yeah.
Then you want to minimize this loss.
Yeah.
Minimize this loss. It's basically maximize the log.
Oh. Yeah.
Maximize log. This is a sigma mode function, right?
Yeah.
And then you want to maximize the cosine difference. Maximize the cosine difference. So maximize the cosine difference is want to that the EI and EJ they are on the same direction, right? Because this one will be, if you say the cosine differences will be larger than equal to -1, smaller than equal to 1, right? They should belong to the range of -1 and 1. This cosine difference.
Oh. Yes. So in order to minimize the loss function, the cosine similarity will reach the maximum. So if the two labels are from the same class, the loss function will be minimized.
Yeah, I think it's basically like the physical meaning of cosine difference. For example, do you mean that if the cosine difference distance is larger, that basically means that the two embedding are more similar?
Yes.
If it is smaller, then basically it will be more unsimilar or more different.
Yeah.
So for those, yeah, I kind of get the point here. I just want to make sure that you understand that.
Okay.
Yeah, just go ahead if others don't have questions.
And finally, to solve the activity recognition problem and on each user, they introduce a personalized output layer parameterized by W. For each user, there is a two-step fine-tuning strategy to adapt the global embedded network into its personalized local classifier. The first, the embedding network theta C pulled from the server is fine-tuned on the local training set of user I to obtain the theta I. And the fine-tuning of the embedded network is also performed with the pairwise loss mentioned before. And the output of the local embedded network is then fed into a fully connected layer for activity recognition. The weight parameters of the output layer for user I are represented by WI, and the WI together with the embedded network are fine-tuned with the cross entropy loss. And this is the second stage of the fine-tuning. As we can see the algorithm here, they first pull the parameters from the server, and this is the first fine-tune strategy. And after this, they fine-tune the W and the theta together with the cross entropy loss, and return the personalized classification model for each user. The data set they used in their experiment are UH-HAR, USCHAD, and a mixture of these two data sets. And also they collect another data set which contain 48 users and 6 activity types. They let 80% of the data set for the training set, and the other for the test. On the UH-HAR and USC data set, one user is used for test, and the rest are used for mental train. And the mixed data set, 2 users used for mental test. And on the collected data set, 5 users are selected as the mental test users. They compare the performance of their proposed framework with these baseline models. The central model is the classification model is trained on all data samples collected on a server. And for the feather average, it applies the original federated averaging method. A global shared classification model is learned in a federated manner. And the feather reptile, the federated reptile is applied to first mental learn a global initialization of a classification model. And then personalization is achieved by fine-tuning the classification model with cross entropy loss on each user. The Meta-HAR CE is a variant of the proposed framework, while each embedded network is trained with a cross entropy loss instead of pairwise loss. They first compare the performance of their framework with a central Fed average and the Fed reptile method. And on each data set, their framework outperform other methods. And they also compare their framework with the Fed average and the Fed reptile on the mixed data set. And the results show that their framework achieved great performance. To compare the different representation learning loss, they compared their framework with the one adopt cross entropy loss. And the results show that adapting the pairwise loss is better than the cross entropy loss.
Yeah, but yeah, can you go back to the, so for this one, you see the first row, the training looks like the first column is the best, right? The mental. So what do we care about, the mental test or mental? So there's two mental tests. What does it mean? One is H, another one is U here.
They tested on the
I think it looks like two data sets, the HSD UH-HAR and the UH-UTSA HAD. I'm not sure. Looks like
Okay. Oh, can you go? Yeah. Maybe I think Xingyue is right. Maybe H. Oh yeah, U is USC HAD, H is HHAR. But then you have to. But if that's the case, you have to. Then for each data set, you should have a train and test. Right now, we can only see one train, but we see two tests.
They all train. They all train. There's two different algorithms. You check the first column, they train both. I mean, the data set use different.
I think it is based on the meta learning. So, I think Tongnian didn't give a background introduction of the meta learning. So, from I know, I just read some papers. So, from I know, the meta learning is trying to first train a part of the model. It looks like a part of the model, and then it can use two different tasks. So that is, so in this case, here they are using two data sets. So after training, they can use to many tasks, and here one data set is a task.
So, but when they train,
they just train one model, and that will be used.
They train one model based on which data set?
based on different data sets, actually.
Oh, you mean they use both data sets to train?
But here I'm not sure. But for the traditional meta learning, when they are train different learners, they will use different data set. For example, if they are doing the classification, for one learner they can use dogs image, and the other learner use cats image, and the other birds image, like this. And then after they have trained this meta learner, and they will do the other task. For example, other task like tiger, something. So
Yeah,
they can like do something like that.
Here they train the model on the merged data set of the UH-UTSA and the USC.
Oh, so they trained on the combined data set.
Yeah.
And then they just test it on one of the data set.
Yeah.
Oh, okay, okay. But yeah, but if you see here, you know, from the training, if you just say about the training accuracy, looks like the Meta-HAR CE using the cross entropy is better than the without using the cross entropy. But if you see the testing accuracy, looks like the HAR, I mean the original HAR is better than the using the cross entropy.
Yeah.
So you mean that what they care is just the testing accuracy? They don't care about the training accuracy, or
I think they only care about the test.
yeah, they care about test. That's normal. Yeah, what we want to observe is, of course, testing accuracy. But for the training accuracy, it tells us how to optimize the model. Whether I optimize the model, you know, sufficiently.
But the accuracy, the difference of the accuracy for the training is not very large.
Yeah, for sure. Yeah. Can you go back to the previous slide? I mean, the other experiment. I want to take a close look at those. Can you go to the first experiment results? No. Okay. So this is the first experiment result, right?
Yeah.
Okay. So they test on those 3 data sets, and they use different algorithm. And oh yeah, you're right. But now, well, you see here, this is the train, this is the test. Their method can outperform centralized one. What happened there? Is this because of the personalization?
I think
Before,
the centralized one, they don't have the personalized output layer.
oh, okay.
Better,
Oh,
yes.
yeah, I get the point. Yeah. It's just a personalization because they have a better.
I do have a follow-up question, like a Dr. Guo question here. So for the federal rapid type, Tongnian, could you specify a little bit more? Because it seems the federal rapid type is similar to what Dr. Guo want to ask. It's kind of centralized training with a personalized output layer. Supposedly, federal rapid type should be better than the Meta-HAR, right? You go to the previous page when you explain those baseline algorithm. Previous page, please. No, yes, this one. I'm not sure exactly what that algorithm looks like, but from the description here, it's a federated learn to classify. Oh, okay, federated not classify. It's not centralized one. Then fine tune for personalization. Well, it will be very similar to the Meta-HAR proposed here, right? So could you talk a little bit more, what's the difference between Federated and the Meta-HAR?
Oh, okay. For the Federated, the personalization is achieved by fine-tuning the classification model with the cross-entropy loss on each user. But the framework they propose, they have a two-step fine-tuning strategy.
Well, then what's the difference between the Federated and Meta-HAR CE? They both use the cross-entropy loss, right?
The Meta-HAR CE, for it is trained when trained the embedded network, it uses the cross-entropy loss. But for the Federated, when they do the personalization, they only use the cross-entropy loss. But
I think you didn't fully address Dr. Pan's question. I think, but you mentioned one point that I thought might be the answer. You said that, well, their approach is more like a two-stage personalization or two-stage file tuning, but the Federated looks like it's just a one-stage file tuning.
yeah,
I guess that might be. I mean, maybe it's not just like the loss. Use a different types of loss. That's one factor, but another factor might be file tune, two-stage file tuning or one-stage file tuning. Can you go to the algorithm? I think when they explain the two-stage file tuning, so that's yeah, I think this is the two-stage file tuning, right?
yeah.
I think Dr. Pan, you say that. I guess okay. I just guess you say they file tune it twice. They first file tune this embedding.
Well, yeah, but still, we need to know a little bit more details about the structure, right? It doesn't matter one step fine tuning or two step or million step fine tuning, right? So you cannot say, okay, 10-step fine tuning is better than one step fine tuning. It's really what do you need for the fine tuning, right? So
I think if Tongnian can show the corresponding code, the pseudocode for Federated, then we will be able to see here.
Yeah, that's true. Yeah, probably that's the best way to answer my question. Yes.
Okay.
So for the Federated, do they learn this embedding network, or do they learn both embedding network and classification model? I mean, here, for example, theta W in your framework, in the paper's framework, they separate them into two parts. So they just use federated learning to learn the embedding network parameter. And now, so Federated, do they use federated learning to learn both theta and W together? You get my point?
Yeah, I get your point.
I think probably Tongnian didn't read the Federated paper, so probably you can address the question offline to us by email or some other way. Yeah. So I do have another question. Could you go to page 18? Well, I'll share the similar feeling as Dr. Guo. I mean, what's this table want to tell us here? Yeah, from the table we can say, the Meta-HAR is better than the CE version for the testing results, for testing accuracy for sure. But you know, what's the things behind this? What's the theoretical things behind this? HAR use the pairwise loss, CE use the cross entropy loss, right? So are you? I mean, are the author trying to tell us, you know, the pairwise loss is better than the cross entropy loss, and the reason why? Also, for the pairwise loss, you define something called cosine similarity, right? There is a multiple way to, you know, measure the similarity between two vectors. So that's the best way, or we can find some other way. No, you know, as long as you know, we can evaluate the similarity, it will be better than cross entropy loss. Is there an optimal approach to do this or something?
For
Let's answer the question one by one, right? Why the pairwise loss is better than the cross entropy loss?
okay. For the cross entropy loss, under the federated learning setting, we need to figure out the global activity set and unify the labels across different users. So that the local model have the same output layer W, and this is time consuming and difficult to realize.
Well, but you implement this and show the results in this table, right? That's the okay, that's fine. But anyway, you take these questions into your mind, right? So think about that. I think the major contribution of this paper is from my side, okay, is two. One is, like Dr. Guo mentioned, it proposed like two-step fine-tuning whatever model, right? So it's better than the existing one, like one step or something, whatever. You know, the architecture is good, it's new or something, right? That's the first one. The second one is they use this kind of a pairwise loss to replace, you know, existing cross entropy loss or some other loss, right? So, but we need to know why it's you know, the pairwise loss is better at least, and if that one is optimal, and improve any kind of room we can further improve that. So I think that's major two contributions here, right? So yeah.
Okay.
But you think about that, right? So yeah, otherwise you just show us a table. I can try some other loss. Then you know, there will be a numerous try, right? So then I don't know.
Yeah, I agree with Dr. Pan. Basically, you maybe they have some heuristic proposed here, but Tongnian, you need to understand under which conditions the pairwise loss is better than cross entropy loss, so that in the future, even if you cannot propose a new loss function, but at least you know in different cases, I mean, for the data set, you may want to use the pairwise loss instead of the cross entropy loss, because the cross entropy loss is what that's the most commonly used.
Yeah.
And then there should be some kind of theoretical reasoning there, or I mean, you need to get the idea there so that, you know, when you design your own model to process some data sets, you know, well, which choice. Otherwise, you have numerous choices, right? So which one should you go with? So that's the I think that's the question here.
They also said that the Powers loss is better when the situation that the local user need that because the Powers law does not require the local users to be aware of the global activity set. And so when there are a lot of users and we don't want them, and there is no global model, then the Powers law should be better.
Yeah. So you are using the explanation in the paper to say that, right?
Yeah.
Yeah. So I know what you mean. Yeah. That's what they explain. But you know, that explain, maybe they understand what they're talking, but for us, maybe we need a more detailed explanation for that point. You know, that's just what they say in their paper. But we need to explain clearly if we want to use that, or if we want to make a presentation to others, because others may have the same question, and if you're using that answer to, you know, to defend yourself, people are still confused.
Probably that's a different mindset from business student and CS student. So
Yeah.
Like business student, they only care about, you know, like what Tongnian mentioned, you know, you care about the customer requirement, you know, as long as you have less requirements on the customer, users can use that's fine. But, you know, for the CS student, we still need to figure out theoretically and technically why this one is better than the other, not only from the, you know, customer or user requirement point of view.
Yeah. I think as long as you, for example, Tongnian, as long as you understand, you know, you don't need to invent a new algorithm. Okay, so this is you know, usually in the business environment, they don't care about the new method, but they do care about the what kind of impact your method can have. I mean, in terms of economic and social impact. So yeah, if you learn, for example, if you say, okay, so this is the method that you are going to use in other data set, but at first you need to understand how the method works, right? I think currently we are still trying to figure out how the method works and what is the advantage of this method compared to original method. I think this is not, no matter whether it's business or CS, you still need to figure out that. The only different thing is that, well, after that step, you can safely use this method, but CS students, they may want to, you know, improve this method.
Yeah.
Yeah, I think now you haven't, we still need to first fully understand this method first.
Okay.
Yeah, but this is a this is a 3W, the web kind of paper. So intuitively, they are more applied. Okay, they are more like I think they are more kind of like applied research rather than the pure algorithm development.
Okay, any further questions? If no, I'm gonna stop the recording here. We're gonna start the stupid question session, okay?